Alright, this is for test 3. We're about to introduce something called Lhopitals rule. Now, in the past we've used algebra, geometry, and trigonometry to try to manipulate it, the expressions, so that we could determine what the limit was. Now we need more direct techniques for theoretical settings or electrical circuits or insulated cables. So this is what Lhopitals rule is all about. If we had more time, I'd tell you an interesting story about it. He's actually a rich person that bought it off of a Bernoulli brother, but you can read about that yourself. Anyway, L'Hôpital wrote the first calculus book. That's why he still gets credit. So we're going to be using my notes, or not my notes, but my wife's notes that she has typed up for this. It's easily read, and so we'll just talk through it. And it's going to be 18 different slides, so we're going to try to go through it relatively quickly. I may have you stop and pause me and write down the things that you want to write down as you go. And then at the end there's some things I wanted to finish up with, things that I thought we should also discuss. So what she means by substituting in here is that if you put a 0 into that, you'd end up with the sign of 0, which is 0, over another 0. And this is going to be an example of what are the indeterminate forms. So the two indeterminate forms you care about right now is 0 over 0 or infinity over infinity. Also, there's proofs of this that I've gotten on Canvas. There's also a proof later in one of the slides here. So there's lots of proofs for this. Okay, not answering the phone. No, this little symbol right here, if it was me writing on the board, I would draw an arrow, and I would say LH, so that you know I've done L'Hôpital's rule. And L'Hôpital's rule says do not do the quotient rule. So no quotient rule when you do this. You're going to take the derivative of your numerator and then the derivative of your denominator. So the derivative of sine is going to be cosine, the derivative of x is going to be 1. Now we can still then take the limit of this expression, and that's going to be the answer. So she has shown the work right here with cosine 0 over 1, and the answer turns out to be a 1. Now we talked about this one previous in some other pictures that we had. I guess I didn't take that picture. Oh well, we graphed it and we used it for identifying the limit as h approaches 0 of the cosine of it, or sine of h over h. And we used that for taking the derivative of a trig function when we did it the long way to introduce that. Alright, so let's go ahead and talk about this one. Let's use a different color. And in this case, if you look, this is going to be a 1 minus a 1 over 0, because the cosine of 0 is a 1, and that's where you get that. That's going to, of course, result in a 0 over 0. So you can only apply L'Hôpital's rule if it's one of these forms. If it's not one of these forms that I've highlighted in the box, then you are misapplying L'Hôpital's rule, and it's going to give you an incorrect answer. You can't use that. So again, L'Hôpital's rule, using the arrows that I would have used, I would have the limit as x approaches 0 of the derivative of sine, or cosine, is negative sine of x, and this is over a 1. And this time when you plug the numbers in, you get a negative sine of 0 over a 1, and that's just a 0 over a 1, or the answer is a 0. So let's keep plugging away at the next set of examples. Alright, we've already done this one, so we're moving on. Alright, if you're to do substitution for this, this is going to be an infinity over infinity. I'd like to talk about this two different ways. If we apply L'Hôpital's rule, then you can see what the answer is going to be, and that is going to be the limit as x approaches infinity of the derivative of 3x minus 1 is a 3, the derivative of an x plus 2 is a 1, and so your answer is a 3. But could we do it another way? And the answer is heck yes, why wouldn't we? This is a rational function, and because it's a rational function, when we take the limit as x approaches infinity, we're talking about the end behavior. The end behavior is going to be whatever we get for the horizontal asymptote. So if you looked at the horizontal asymptote and looked at the dominant terms, you're going to end up with a 3. Now you may say, why would I want to do that? Lhopitals rule is perfectly fine for me. But let's just look at another example and you tell me what you're going to want to do. If I was to take the limit as x approaches infinity, and this is a 7x to the fourth plus a bunch of other stuff, 17x squared minus 4. And this one is a 5x to the fourth minus 3x cubed plus 4x squared plus 7. If you were to apply Lhopitals rule to this one, then you'd have to apply it 4 different times before you can eventually get your answer, like we got an answer right here. But if you just simply look at the horizontal asymptote, the horizontal asymptote is just simply take the dominant terms and figure out that those reduce out and you end up with 7/5. So I would much rather do horizontal asymptote than Lhopitals rule in this particular instance. It would save me 4 different levels of taking a derivative. And one more thing to make sure that you've got it, let's just talk about what would happen if I had to take the limit as x approaches infinity of a 2x squared plus 3x plus 5 over an x cubed minus 3x plus 1. Well, if you look at the dominant terms this time, don't you dare tell me that this answer is going to be a 2. Because when you reduce it, you get 2 over x, and you're supposed to remember the horizontal asymptote is 0, and that would be your limit for that thing. That is your answer. So horizontal asymptotes still need to go on the gravestones. All right, so, well, look at that. I didn't mean to do one quite like it, but forget the Lhopitals rule. If I find the horizontal asymptote, my answer is going to be 7/2, and I am done. I don't need to do it the other way. So we'll keep going. All right, so when you look at this particular example, you end up with a 2 minus 2 over a 2. And the question is, may you use Lhopitals rule? And the answer is no. This is a 0 over 2, and your answer is just going to be a 0. So no Lhopitals rule. It's like taking a hammer to a screw. You don't want to use the wrong tool for a particular question. And then as far as this one's concerned, if you were to do this by substitution, and you can, you'd end up with 4 plus 2 minus a 6 over a 2 minus a 2. And that's going to give you a 0 over 0. We did this another way. We factored, but you could apply Lhopitals rule to this thing. When you apply Lhopitals rule, you end up with 2x plus 1 over a 1. So when you plug that in, you end up with 2 times 2 plus 1 over 1. This is going to work out to be a 5. So you can use Lhopitals rule now and forevermore. You don't have to do it by factoring. But just to remind you what you did back in Calc 1, earlier in Calc 1, back in January, which seems like years ago, you could have factored that, and I'm just going to go ahead and factor it. That's x plus 3 times x minus 2. This is all ringing a bell. Over x minus 2. These things reduce out, and then if you plug that in, you end up with 2 plus 3, which is, oh my goodness, it's 5. Amazing. So you can do Lhopitals rule if you want to, or you could do it by the way you did before, but some of you are not quite so good at factoring, so you might want to reconsider that method. You can do Lhopitals rule to accomplish the same thing. So I'm on slide 4, better keep going. All right, here's another situation that you'll see, and you'd have to remember how to graph cosecant and cotangent to help you with what's going on here. But if you were to graph cosecant, you'd have a vertical asymptote. Let me draw it with a different color. You'd have a vertical asymptote at 0. You'd have a vertical asymptote here. You'd have a vertical asymptote here. And so when you graph cosecant, and that's at 1 and that's at -1. I didn't do that very well, but you get the idea that if you head towards 0 from the right, then 0 from the right, this is headed to infinity. And then as far as cotangent's concerned, the graph of cotangent is going to be, again, vertical asymptotes. And when you graph that, it's going to look like this over that one period. And as you approach that from the right, that's headed to infinity. So what you end up with is an infinity minus infinity. And this is a new strategy that you need to remember to do. So anytime you have infinity minus infinity, what you want to do is you want to add fractions. Okay, so this is not in a form that we can apply Lhopitals rule yet, but we're going to rewrite this as a fraction. And cosecant's the same thing as 1 over sine. And cotangent's the same thing as cosine over sine. And so when you add those together, 1 minus cosine of x over sine of x, because you remember when you add fractions and they have the same denominator, you just recopy the denominator. So now if you plug that in, you're going to end up with a 0 over 0, which means you can now apply Lhopitals rule. So we're going to do our little arrow and apply Lhopitals rule. And when I do that, the derivative of 1 is 0. I don't need to mess with that. The derivative of cosine is negative sine. And then the derivative of sine is going to be cosine. So if you look at the answer to this thing, this is going to be the sine of 0 over the cosine of 0, which is going to be a 0 over a 1, and your answer is going to be 0 for this thing. But you might need to find some more examples of this and add this later. I don't know. Maybe write it up and send it to you if I don't have more pictures or more examples of it. But you will definitely need to go through this process. So you have to add fractions if you have infinity over infinity, or infinity minus infinity, I should say, so that you can go ahead and apply Lhopitals rule. You cannot apply it until you get to this situation right here of 0 over 0. Time for a break. Alright, to help you figure out what's going on here, it's kind of important that you graph. If you don't know how to graph, then you're going to have some issues. And so here's what I'm talking about. We're supposed to be looking at this x, I'm talking about this expression over here. The limit is x times the tangent of 1 over x, and x approaches infinity. So the way I analyze that is, here's x approaching infinity for the 1 over x. What is that doing? Well, it's making my y's get smaller. My y's are headed towards 0 from the right because it's going to be a half, it's going to be a third, it's going to be a 1/5, it's going to be a 1/10, it's going to get extremely small. So in essence, what's happening then is this graph right here, because it's headed towards 0 from the right, is causing our tangent, then as x heads towards infinity, the tangent of 1 over x is going to head towards that 0 from the right, which is headed towards a 0. And then as far as this part of the expression is concerned, that's infinity times 0. So anytime you have infinity times 0, the strategy that you employ is you have to rewrite it as a fraction. So rewrite as a fraction is the strategy. And when you do this, sometimes you actually have to make a complex fraction to accomplish the goal. So don't be surprised if I make them, even though I'm allergic to them, I will make a complex fraction. So how in the world do I do something like that? Well, let me get a different color and I'll show you. I think I need blue today, this time. So I have the limit as x approaches infinity, and I want to rewrite this as the tangent of 1 over x, but that x that you see right there, that needs to go in my denominator is 1 over x. So what's happening now is that this is a 0 over 0 situation. When I rewrite this as a fraction, even if it means make a complex fraction, I'm going to do that. Because it's 0 over 0, I can apply Lhopitals rule. So please remember that 1 over x is the same thing as an x to the negative 1. So when I take the derivative, I don't have enough room to do everything over here, so I'm just going to do it, but I'm taking the derivative of x to the negative 1. So when I apply Lhopitals' rule to this, I'm going to have the secant squared of 1 over x times then a negative 1 x to the negative 2 when I take the derivative of this x to the negative 1. And I'm going to do the same thing here. I'm going to end up with a negative 1 x to the negative 2. And lo and behold, what will happen is these things reduce out. And so now I just have to take this limit. Let's go back to blue. And this limit is going to be the secant squared of basically 0, which we all know is going to be the same thing as 1 squared, or we get an answer of 1. So this infinity times 0 situation gave us a limit, and it's going to turn out to be a 1. Now, the limit or Lhopitals rule is something you all are going to use in Calc 2, and if I see you and you don't have a clue, then guess what? Especially when we have them on the test, I'm going to know that you didn't do what you needed to do to make sure you learned it, or we need to make sure that we review it again when we get to Calc 2. But regardless of whatever the reason is, we need to know these processes. So it'd be to your benefit to get it under control here in Calc 1, even through these terrible, nasty circumstances of what we're doing right now. All right. So anyway, you can kind of see this here when infinity times 0, then the strategy is to create a fraction. It's a fraction. Sometimes it's a complex fraction. It's not always a complex fraction. So let me move that back, and you can have that whole screen then. All right, let's keep going. I think I'll go back to black here. And so if I look at this one, this is a similar situation of, if I try substitution, I'm going to end up with pi minus pi over 0, which is just a 0 over 0. So I can apply Lhopitals' rule to this thing. And so when I take the limit as x approaches a pi halves, I would have a 2 over a negative sign of x. So that's going to be 2 over a negative sign of pi halves. And all my trig and pre-calc students, you darn well better know that that's 2 over a negative times a 1. So you get an answer of a negative 2. All right, so here we go. We're going to keep going, but when we do this next example, I'm here to tell you the answer is going to be 2 because I look for the horizontal asymptote. And I'm done. Not because I'm the math teacher, I'm trying to tell you that's the power of the horizontal asymptote. But let's pretend we don't see that. So when I apply Lhopitals' rule to this, if I'm supposed to, this is going to be a 0 over 0 plus a 0, so yes, I can apply Lhopitals' rule. I don't need to, but I can. This is going to be a 2, and this is going to be 1 over 7 times 1/2 x to the negative 1/2. And I'd be willing to bet some of you don't know what that expression would be in that situation. Well, it's a 2 over 1 plus 7 over 2 the square root of x. And that's going to work out to be 2 over 1 plus 7 over 0. And let's see. I can't do that. I got to do something else. I got to multiply this expression to get rid of the complex fraction is what I have to do. So let's see, what should I do to get rid of the complex fraction? So I think I'm going to erase this. Don't really want this anymore because I don't have enough room to keep it. So I'm going to multiply by, let's see, how about if we just simply did a square root of x over square root of x multiplied together here. So let me get rid of that equal sign because it's not there. We're multiplying to get rid of the complex fraction. All right, let me erase my prediction here of horizontal asymptote because I need the room. But anyway, so I'd have the limit as x approaches 0 of, and I would have 2 the square root of x over what would amount to a square root of x plus 7 over 2. So as x heads towards 0 again, I have a 0 over 0. Okay, I guess I get to admit to being a big dummy. So the answer is going to not be what I predicted. I'll tell you why I was wrong to begin with. But anyway, let's finish this problem. The answer is going to be a 0 when it's all said and done. So 0 is the answer. So what was my mistake when I predicted the other? Well, I can tell you what my mistake was very easily. The limit as x approaches infinity of that same expression, that I would bet the farm, and I would bet you, that thing is going to work out to be a 2. And so my mistake was, I was thinking of infinity because we had just done one last page, and this one is the limit as x approaches 0. So I'm sorry, this is the correct answer for this particular problem right here. And I did all the steps correct, but my prediction was wrong, way wrong. Hope you're having a good laugh for this, but I'm not that concerned. I'm glad I make you happy. So we shall move on then. Alright, so here's another one that you end up with the 1 over x, which is headed towards a 0, it's headed towards an infinity, and I'm thinking the wrong thing again. And this one is also headed towards an infinity. If you're saying, I don't understand why that's headed that way, look at what 1 over x looks like. Here's the graph of 1 over x. And as you head towards 0 from the right, this is headed to infinity. Now what in the world is the graph of 1 over x, the square root of x? Well, it's not quite the same thing, but it's very similar to this in the fact that you're going to end up with only one part of this because it's not defined for anything. The domain is what I'm trying to say, is the domain is going to be from 0 to infinity for this. So you don't have the second part. You don't have this part over here that the other shape had. So there's only this one part that you see right here. But it's headed to infinity as well. That's the key thing. So what we're going to need to do is we're going to need to add those fractions together like we discussed before. So this is another one that's infinity minus infinity. So if I find a common denominator, hopefully you guys are not still allergic to fractions like you were before spring break. But this is going to be the same thing as the square root of x over x the square root of x minus, and this is going to be x over x the square root of x. And so what will happen when you add these together is you're going to have the limit as x approaches 0 from the right of the square root of x minus x over x the square root of x. And so what's happening with this is you have a 0 over 0, and you can apply Lhopitals' rule to this. So when I apply Lhopitals' rule, I'll have a 1/2 x to the negative 1/2 that's for the first one, minus a 1 over, and I get to do the product rule for this denominator. So that's an x times a 1/2 x to the negative 1/2 minus, and it's going to be the x to the 1/2 times a 1. Guess what we should do? This is a la Romina. We need to factor out, I guess I need a different color to do the factoring. I need to factor out an x to the negative 1/2 out of these two expressions. Okay, I'm talking about here and here. So when I do that, I will just do it in red. So this is not Lhopitals rule. I'm just going to do some algebra here. This is going to be the same thing as what amounts to 1 over 2 the square root of x minus a 1, there's the numerator, over, and when I factor this expression, I'm going to factor out an x to the negative 1/2. That's going to leave me with a 1/2 x minus another x is what we're going to be left with. Alright, so let's resume here, and let's change colors. What I did is, I went ahead and simplified this expression down here, and that's the same thing as 1 over 2 the square root of x minus 1, that didn't change. But this is the same thing as if I take 1/2 x minus x, that gives me a negative 1/2 x, and let's see, then the x to the negative 1/2 ends up coming down here. So that's how I simplified that part of the expression. So I decided let's get rid of the complex fraction by multiplying it by 1. So the common denominator for 2 the square root of x and all these fractions is 2 the square root of x. So when I distributed it here, it got rid of the fraction. Here it gave me, well actually it gave me a not just a 1 square root of x, it's this 2 the square root of x. And regardless, it doesn't matter, it's still going to be 1 minus a 0 over a 0. The answer is this silly limit does not exist. So anyway, all that wonderful work and that limit does not exist because we don't have Lhopitals rule anymore. We can't keep applying that. Alright, so I did some preliminary work here before I started yapping. So what I wanted to do is talk about the graph. And so the graph of y equals a tangent of x is going to be this equation. And I managed to destroy this vertical asymptote right here, which is x equals pi halves. So as you head towards pi halves, this is headed towards infinity. And this was not stated, but we might have wanted to state that this is going to be x approaches pi halves in the negative direction. So that might be a typo that I need to mention. Alright, so anyway, regardless, if I change that to as it approaches pi halves from the left, we're going to end up with a 0 times 1 over 0. Oh, before I forget to do that, I have, when I do the limit as pi halves approaches from the left, I get the opposite of 0, which is just a 0 times infinity, because that limit as the x approaches pi halves from the left is going to head towards infinity. So I need to rewrite as a fraction. So that's that strategy of rewrite as a fraction. And I did not have to write it as a complex fraction. It's just write it as a fraction. So I accomplished that by rewriting tangent as sine over cosine is what I decided to do. Now if you evaluate that, you're going to get 0 times 1 over 0, which is going to be a 0 over 0, and you can apply Lhopitals rule to this. So when you apply Lhopitals rule, you're going to have to do the product rule up at the top. So this requires the product rule. And when I do that, I recopy the first times the derivative of the second, recopy the second times the derivative of the first. And so I'm going to end up with that numerator. Take the derivative of my denominator, I get a negative sign. And honestly, I'm ready to plug numbers in. So when I plug the pi halves in, this becomes the opposite of 0 times a 0, the cosine of pi halves is 0, plus a 1 times a negative 1 over a negative sine of 0, or pi halves, which is a 1. So basically I end up with a negative 1 over negative 1, which gives me a positive 1. My answer is positive 1. Alright, the last kind that we have, and that is going to be the kind where you have 1 to the infinity, 0 to the 0, or infinity to the 0. Anytime you have these three different options or possibilities, you have something that can be put in an indeterminate form if you follow the steps. That is, you're going to do a substitution. So you have to do a substitution of y is equal to whatever the argument is that you're taking the limit of. And then you're going to take the natural log of both sides. And once you've done that, you're going to find out what situation may be. And usually it's going to be infinity times 0. So you're going to have to rewrite it as a fraction. And once you rewrite it as a fraction, then you can apply Lhopitals' rule at that point after you get this situation. And then, once you are done with the whole process, you still have to resubstitute. So, if I had to write the steps here, I would substitute. I would take the natural log of both sides. I would look at whatever limit situation that I have, and whatever limit situation, it is usually 0 times infinity or infinity times 0, and that requires you to have to rewrite it as fractions, as a fraction. So, and then the last few steps is that you find the limit after you rewrite it, and then you have to resubstitute. So these are the steps that I'm going to go through when I go through this process. I don't think it's just 3, it's these 5 steps that you see. So at some point when I need space, I'm going to erase them. My suggestion is you pause this. If I need space and I erase it, then you would have paused it and written these steps down when you have these cases up here. All right, so let's go ahead. I think we need a different color to start this out. And so if you look at what's going on here, this is a 1 plus 0 to the 0 power. And so you have a situation of, well, let's start that over again. Okay, this is going to be an infinity to the 0 power. The reason for that is that as you head towards this part right here, 0 from the right, that's headed to infinity. I'm using this graph again, and I'm heading towards 0 from the right. So that is headed to infinity. So 1 plus infinity is really going to be that right there, and that's going to be infinity to the 0 power. All right, so let's try this again and keep going. But this is going to be infinity to the 0 power. We're talking about this case right here, right now. So step 1 that I was talking about is we're going to do a substitution where I have y is equal to 1 plus 1 over x raised to the x power. Then we're going to take the natural log of both sides. And then I'm going to rewrite the right side as, and this is where I have to use properties of logarithms. So I would have x, the natural log of 1 plus 1 over x in that situation. And so when I take the natural log of both sides, we're going to have to rewrite using the third property of logarithms. So there's an extra step there, I guess. So I'll leave that up there, but I would just incorporate that as when you take the natural log of both sides, eventually you're going to have to rewrite that using the third property, and this is what I did from here to here, is the third property of logarithms. All right, now if you would examine this and take a limit of this thing, and I'm definitely going to need to erase over here for those steps in just a few minutes. This is going to be what amounts to a 0 times an infinity situation. All right, so because of the fact that you're taking the natural log of infinity. So a lot of graphing here you have to think about and do. So I need to rewrite this as a complex fraction, and I'm going to write this way. And before I actually apply Lhopitals' rule, You see, I did make it a complex fraction. I need to erase all of the stuff that's over here on the side. So if you need it, you better stop me right now, pause it, and pause the video and write this down because it's about to go away. So I need to erase all of this. I really don't need to underline all that so heavily, and let's get rid of the stars. Alright, so we're continuing to talk here, so I want to do something else before I get started with the Lhopitals rule. I want to rewrite this as the limit as x approaches 0 of the natural log of 1 plus x to the negative 1 over x to the negative 1. So now I'm going to apply Lhopitals rule. I think we need another color. So I'm about to apply Lhopitals rule to this expression right here. And I better use a different color than that. So that means I'll have the limit as x approaches 0 from the right. And this is going to be 1 over 1 plus this x to the negative 1. And this is going to be a negative x to the negative 2 over negative 1x to the negative 2. And this is going to reduce out. And if I take this limit, this is going to be a 1 plus it's going to be a 1 over 1 plus an infinity situation. So I really need to clean up the complex fraction. So I need to erase this straight. And I'm going to go ahead and clean that expression up. So when I write it, the limit as x approaches 0 from the right of what amounts to a 1 over 1 plus 1 over x. And I want to multiply by x over x to get rid of the complex fraction. So what I'll have then is the limit as x approaches 0 from the right of an x and a x plus 1. And this situation is going to turn out to be a 0 over 1. So this thing works out to be a 0. So lo and behold, we got this answer, but I have to resubstitute. You cannot stop there. So let's see, I guess I need another color. So when I resubstitute, I have the natural log of y is equal to a 0. When I do this by definition of a logarithm, this is y is equal to e to the 0 power, which is equal to a 1. So this whole expression is equal to a 1. Alright, so let's continue and see what we're at. Alright, in this case, it looks like we have a 0 to the 0 power, which is another situation that we described before. So we need to see what's going to happen with this. So I'm going to go through the steps again. And the first step is to let y be equal to x to the x. Second step is take the natural log of both sides. Third step is, or part of the second step, is to rewrite it using the third property of logarithms. Okay. Now, if I take the limit of this thing as x approaches 0 from the right, if I graph y equals the natural log of x, you have a vertical asymptote right here at x equals 0. So as you head towards 0 from the right, then this thing is headed to negative infinity. Headed to negative infinity. So what this means to you, when I go back to black here, that I would have x, the natural log of x, is going to be headed to 0 times negative infinity. It doesn't matter what kind of infinity you have, you're going to be doing that step where you're going to rewrite it as fraction. You're going to rewrite it as a fraction. So we're about to do that step right now. So I'm not doing any Lhopitals rule yet. I'm just rewriting it. It's the natural log of x over, and I want to write this as x to the negative 1. It's the same thing. Basically, you're going to end up with a negative infinity over a positive infinity. You say, well, how do I know that? Well, you're supposed to remember this graph that we have talked about many times earlier. So as I approach 0 from the right, it's headed to positive infinity for that graph. So, good news. I can apply Lhopitals rule. So let's do a different color. I need another color. So when I apply Lhopitals rule, I would have the limit as x approaches 0 from the right of a 1 over x and a negative 1 x to the negative 2. Alright, that's what we have. Now, I don't want to work with this. I want to go ahead and simplify this and do some algebra to it. So if I do algebra, this is like an x to the negative 1 over a negative 1x to the negative 2. And if I simplify that using my properties of exponents from intermediate algebra, you're going to end up with a negative x to the first power. Okay, because when you subtract exponents, you end up with here, let me just show it. A negative 1 minus a negative 2 is going to give you this limit as x approaches 0 of what amounts to a negative x to the first power. And this thing is going to turn out to be a 0. So we're ready to resubstitute. So I would have the natural log of y is equal to a 0. By definition of a logarithm, this is equal to a 1. So this answer is another 1. Gee, it looks like everything is always going to be a 1. And the answer is, don't you dare think that. I have other examples that are coming that will hopefully clarify any situation such as that. Time for another drink of water. Alright, let's keep plugging away. I've got 5 more slides, I think. One of them is just a proof, though. So anyway, so if you substitute this in, which I decided to do before I started yapping again, this is going to be an infinity, because e to the infinity power is going to grow forever, because I'm sure you remember what e to the x looks like. All these graphs that I've been preaching since college algebra, some of you need them with a nice, beautiful horizontal asymptote at y equals 0. Anyway, regardless of that, this is going to be an infinity to the 0 power. I'm not even going to talk about the negative 2 over infinity being to the 0 power. So we have to do substitution. So let's make y equal to this e to the x plus 1 over a negative 2x to the negative 1. Let's do some preliminary work here. Take the natural log of both sides. Use the third property of logarithms, and so the natural log of y is equal to a negative 2x to the negative 1 times the natural log of e to the x plus 1. If you bother with this, this is 0 times infinity. You can check that on your own. I'm not going to argue that point. And so what we need to do is take the limit as x approaches infinity of this expression, which we already said if I do it, take a limit as x approaches infinity, it's that. So I'm going to jump to the rewriting part of this. Put the negative there, and I'm going to put the 2 there, and the x to the negative 1 goes down here as an x to the positive 1. So what we have is an infinity times 2 over an infinity. I can apply Lhopitals rule. So I have the limit as x approaches infinity of 2 times, oh yeah, there's a negative in front of all this, 2 times 1 over e to the x plus 1 times another e to the x, once I take the derivative using the chain rule. And down in my denominator, I just simply have a 1. So if I went ahead and simplified this expression before I worry about trying to do anything else, this is a negative 2 over e to the x divided by e to the x plus 1. Alright, you can apply Lhopitals rule again if you want, because this is infinity over infinity, but I'm here to tell you this is the wonder of horizontal asymptotes. I think we need a nice pink for this one. This is e to the x over e to the x. If I take those dominant terms, my horizontal asymptote is going to be, I hope you can read this, it's going to be a 1. Last time I used pink. So this thing is going to work out to be a, oh come on, give me a different color. It's going to work out to be, if I don't bother with that, or let's erase it, get it out of there, it's going to work out to be a negative 2 times a 1 or a negative 2. That's what that limit would be. But I'm not done yet because I have to resubstitute. And so when I resubstitute, I have the natural log of y is equal to a negative 2. And by definition of logarithms, not Lhopitals rule, by definition, this is y is equal to e to the negative 2 power. Yay, it's not a 1, and it's not a 0, and it's not a, does not exist. It's a different kind of number, and you will see more of that soon enough. So again, there's another example, time to push on. Oh good, we're getting close to the end. This is the proof, or at least one of the proofs. I've given you other proofs on Canvas of Lhopitals rule. Basically, it's using the definition of a derivative that we had the alternative definition of a derivative. Okay, we did that back when we learned about derivatives. And I did that because I knew we would need this for this proof down the road at some point in time. So anyway, we're working backwards. We're working from the right-hand side to the left-hand side is what's happening. And this is what is called the weaker form of Lhopitals rule. I have another proof of the stronger form, but at this point I don't really want to talk about them anymore. I just want to keep going. Oh good, I've already done this stuff, so let's see, what's a good color for you to highlight and I can point things out? How about bright green? I think that's a good color. So if you were to look at this particular problem, oh my gosh, it's the same stinking problem that I did before, except it's got an e to the x plus 3x. So it's not quite the same thing, is it? It looks the same, but it's not the same thing. And so limit as x approaches a 0. Alright, so if you examine what's happening here, you end up with e to the 0 plus 0, and it's raised to the infinity power because you have to remember what happens with this graph right here, as we've discussed before. If you can't visualize the graphs, then you're not going to know what this situation might be. And so you're putting yourself tying your hands behind your back because you didn't bother to learn those basic shapes back in pre-calc and college algebra. Anyway, so I'm doing the steps. Here's the first step where I do a substitution. Then I take the natural log of both sides. Then I use the third property of logarithms. There they go. There's the 3 steps so far of the steps that I wrote on the page. Now that I have that, I can apply Lhopitals rule. Okay, and when I apply Lhopitals rule, generally what happened here, if I'd have bothered to do it here, it would have been infinity times a 0. Actually, the way it is right now, it would have been an infinity times a 0, and so this really didn't happen. This is what happened right here. Whoops, I didn't mean to erase it. This is what happened. Well, it looks better now anyway. So I'm getting a little punchy at this point. Hopefully you can hang with me. I'm trying to keep these lower than 60 minutes. So I have the 0 equals, or 0 over 0 situation. Apply Lhopitals rule, so I took the derivative of the natural log, and then I took the derivative of what's inside by the chain rule, and I have this. And I went ahead and just plugged numbers in, and this answer right here is going to work out to be a 4. But that's not the answer because I have to resubstitute. And then I get actually I think the resubstitute is the 5th step. The actual finding is the 4th step. But I resubstitute by definition of a logarithm. I know that this is y is equal to e to the 4th power, and there's the answer to the original question. So these are examples that I have in my set of examples that my wife doesn't use that I wanted to make sure I included. Here's another question. It's Adrian Ponte's question. Actually, Adrian Ponce's question. He always said, well, my teacher said any number to the 0 power is 1, and I tried to tell him, and I would tell you the same thing, that your teachers in algebra lied to you. Any finite value to the 0 power is 1. Finite values are anything that's not infinite. So you can't go by that. You have to see what's going to happen. And there was a lot of examples where we did this, and oh my gosh, we got a 1. And so Adrian kept asking me, well, you didn't prove it to me. So I found this example. So here's my proof to you guys. So you have the first step is do the substitution. Second step is to take the natural log of both sides. Okay. Third step is I went ahead and rewrote it because I knew that's just the third property, I guess. I think it's part 2 of step 2. Anyway, and we get a 0 times infinity. I don't need to worry about this because, let's see, this is definitely a 0, this first expression, this is definitely an infinity. All right, so when I rewrite it, and I went ahead and did the limit again here, but I'm just kind of jumping the gun knowing that I'm going to end up with infinity over infinity. And so I apply Lhopitals rule because I can. And when I take the derivative of this, it's 1 over 1 plus 2x times the derivative of what's inside by the chain rule, and that's going to be a 2 right there. If I take the derivative of 2 natural log of x, I recopy the coefficient, take the derivative of natural log of x, and that's just a 1 over x times a 1. So I can work and do some algebra to this thing, and this is what I got. And I decided I'm tired, I don't want to write this out again. But if you look, it's simply going to be an x over a 1 plus 2x. So just look for this as a horizontal asymptote, like it's a a rational function. And so your horizontal asymptote is going to be 1/2. Okay, then you have to resubstitute. And when you resubstitute, you have the natural log of y is equal to 1/2. And there you go, Adrian. Y is equal to e to the 1/2. It's not equal to a 1. I told you your algebra teacher lied to you. If you think I'm getting punchy, you're right. All right, here's another one that's an infinity minus an infinity, and you can't add those fractions together. Good luck with trying to do that. That's the supposed strategy, is to add fractions. Well, you can't. But you have another strategy that I wanted to mention to you, and that is log properties. And this is the second log property because you have one log minus another log, which means you can write it as the natural log of the positive one goes in the numerator, and the natural log of the negative one goes in your denominator. And oh my goodness, we can find a horizontal asymptote for that, and that's just a 2 if I just look at this as the expression y equals 2x over x plus 1. And that's another beauty of horizontal asymptotes, is I can do that and it doesn't change a darn thing for the answer, and we're going to still get the same answer without doing all the excess algebra. That's why it's going on the gravestone. So if that's a 2, then this limit right here is going to be the natural log of 2, and I'm done. Nothing else to be said. And oh yeah, these pictures are for those of you that are college algebraically challenged or took college algebra before SOASH. You need to recognize that as you head towards infinity, that the natural log of that and the natural log of that is both headed to infinity. That's why you get the infinity minus infinity. All right, so last but not least, I promised my college algebras that I would prove to them that the compound interest formula that you see right here, and I want a different color, let's do orange. This is your compound interest formula that you use when the interest is compounded n times a year, like monthly or quarterly or daily or whatever it may be. Well, we want to talk about how do I get a formula for compounding continuously, which means that we're doing n an infinite number of times a year. How in the heck do we do that? And I promised my college algebras, and maybe I promised to you my pre-calcs, that I would prove the formula for you, that how this formula turns into the shampoo formula. Need a drink. All right, so let's finish strong here. When you look at this, the only variable that you have is n. That's the only variable that you have. The p, the n, the r, the t are all treated like constants. So n is the only thing that's going to change. So what we're going to do is take the limit as n approaches infinity is what we're about to do to this thing. Now, some things happen with limits that maybe I didn't talk about at some point, but I'll tell you now. That a constant can be placed in front, and it's kind of like just recopying the coefficient when you take a derivative. You're just going to recopy that, and it's going to be times whatever the limit turns out to be. So we're worried about taking the limit as n approaches infinity of this expression, which is going to turn out to be 1 to the infinity power. So we're going to do our steps. We're going to do our substitution. We're going to take the natural log of both sides. We're going to go ahead and recognize that if I take the limit of this expression right here, it's going to be infinity times 0. So I write it as a complex fraction. And when I do that, I get 0 over 0, so I can apply Lhopitals rule to this thing. Now, there's something else about this that you should note, is that the t, I pulled that out because it's just a constant. And so I really only worried about, oops, I didn't. I need to fix that. I need to erase. Oh, don't do that. I need to erase, not that whole thing. Anyway, what I was trying to discuss here is that the t was put in front, and the n I wrote as a complex fraction right here. So that was botched up, and I'm glad I fixed it now. All right, so I'm going to apply Lhopitals rule here. That's what I showed you with this. And I have the t on the outside, and I'm taking the derivative of what's on the inside of the parentheses here. So again, the t can go out in front, just like the p went out in front before. Talk about this p back way over here. All right, so when I do Lhopitals rule, I'm going to end up with this 1 over the original argument times the derivative of the 1 plus r to the n, and I decided to save some time here for this thing. This is going to be a negative 1r n to the negative 2. And if I take the derivative of this, it's going to be a negative 1 n to the negative 2. And then things reduce out. This reduces out. These two negatives right here become a positive right here. So this whole expression then turns into just an r. Now, what are we left with after I take this limit on this step? Well, the limit as n approaches infinity is going to be t times 1 over 1 plus 0 times the r, and I'll get out of there. We get tr. But then I have to resubstitute. So I resubstitute natural log of y is equal to tr. By definition, oops, forgot to write that. Y is equal to e to the tr, so that means then that this is e to the tr, or I could write it e to the rt is what I decided to write. Why did I do that? Because I want to go back to the original expression right here, and I think I really need another color for this. I want to go back to this expression right here, and I have the p recopied, and I figured out that this limit for this part right here is going to be e to the rt, and there is your shampoo formula. So even though we have a disease going around, I lived up to my promises. I've shown you how compound interest continuously formula turns into p times e to the rt power. Hooray for me. All right, I am done for this moment. I need a break. Made it before,